Did you want to go?
Yes. Okay, welcome everyone to the Privacy Enhancement and Assessments Research Group, to our IETF 115 meeting. As always, there is the note bar, which I'm sure you're familiar with by now, and we want to make everybody aware that the session is being recorded. And we also just want to note that the code of conduct that applies to the IETF also holds in these meetings as well. A few extra notes for in-person attendees. You're required to have your mask on at all times in the room, apart from when you're actively speaking. For in-person attendees, can you also sign in through the Meet Echo Lite client, because that replaces the blue sheets. And in following what other groups have been doing, we'll be using a single queue in Meet Echo, including for people in the room. So if you have a question, please add yourself into that queue via the tool rather than going directly to the mic. We have a very slightly modified agenda from the one that was published on the data tracker. Due to slight uncertainty of one of the authors being able to attend for the draft updates, we will be going through those updates at the start of the meeting and then moving on to the remote presentations. I believe we have a minute taker, so thank you, Gershabad, for that. Before we get going, is there anything anybody would like to add or change about the agenda? Okay. No, if not, then we will start by just running over a quick update of the drafts that we have going through the research group at the moment. Updates, yep. Through a review of drafts that have progressed from the research group, we have a pair of drafts on the history and the generation of transient numeric identifiers. We believe they are in the final throes of review, and we're hopeful we're one update away from getting those published, which will be very nice. They'll be the first documents to come out of the research group. We also have the Survey of Worldwide Censorship Techniques, which passed its last call a couple of months ago and has now been sent on to the IETF chair for further review. And we currently have two. Oh, Colin.
And
yes.
the IETF chair apologises for being slow at reviewing that, but I'm hoping to get to it soon.
Lovely. Okay, thank you. Yes. And hands up from Mallory. Yay. Thank you. In terms of documents that are being actively worked on, we have two at the moment. We have the guidelines for performing safe measurement on the internet. That had a fairly recent update in, I believe, August of this year. Thank you, Mallory, for that. And we think that's in relatively good shape. We would love some more review of it, but we think we could consider moving that forward in hopefully the not too distant future. The other draft that is actively being worked on at the moment is one on IP address privacy consideration. This is a document that came out of the interim we had on this topic year before last. We have several authors contributing to this at the moment, and I'm hoping that Brad is available to give us a word or two on the status of that. If
Yep.
you can.
Hi all. At this point, we published a new version of the draft last week, and we think we have some good content there, although it is in bad need of solid editorial pass to make sure it is helpful for current topics that folks are looking to use the draft for. Really looking for folks to take a review, let us know what applications of the draft that where that could be helpful, and we'll be working on that editorial pass between now and 116.
Thank you, and thank you for stepping in at the last minute to update us on that as well. Mallory, I saw you sneak into the queue and missed you. If you want to go ahead.
Hi, Mallory Nodal, CDT. I just wanted to update really quick on the safe measurement because I appreciate your faith that this document is good, but there are actually some important parts of it that are unwritten, or in my view aren't elaborated enough. So if there are folks who work on this, I could also, with maybe encouragement from you all, send messages to folks in like PPM or elsewhere that might have some overlap here, just to get, I think, better text in those places. That would be much appreciated. So you can reach out to me directly, or you can go on the list. And then the other update on that draft is just that at the IAB workshop on measurement in encrypted networks, I talked about this draft a bit. So others have seen it, and it was sort of in the context of like, it doesn't exactly speak to that workshop's mission or statement, but I thought that what was in that draft isn't really anywhere else in terms of how you kind of do harm reduction holistically, rather than just worrying about, you know, what specifically you're sending or what you're measuring, I guess, of what's sent. So that was well received in the sense that folks found it useful, and so I wanted to feed that back to the group as well. Thanks.
Thank you very much. And as always, we're looking for new work, so please get in touch or write to the list if you think you have other items the group would be interested in working on. Okay. Okay. Oh, their slides have stopped moving. There we go. Okay, so I think we are now ready to move on to the presentations. If we can do that. And so the first presentation today is by David Oliver. It's on clean insights. And we have a 20-minute timer on this, including time for questions. Okay, let's just wrangle your slides.
Thank you. Are we all seeing that?
Yep, please go ahead.
Okay, very good. Well, I'd like to thank the chairs for asking me to, for inviting me to present. And so here we go. I put a TLDR in the front here because some folks in the room may be very familiar with privacy preserving measurement, especially the activities at IETF or from other areas. And there's going to be some folks see this presentation outside the room, so I thought I'd add that here. But we can move right along to our origin story for Clean Insights, which is that we started in 2017 with a hackathon project at the Harvard Berkman Klein Center in association with MIT. Now, it's hard to remember this at this point, but the European Union's GDPR had been adopted but was not yet in force at this time. So we didn't have a lot of insight into how that was going to roll out. And there was interest across a set of communities who were involved in civil society and internet freedom and human rights in what was going on with measurement and how measurement intersected positively or negatively with privacy and human rights, et cetera. So I think you'll notice the date down to the next item where Internews, a nonprofit who funded our work later on Clean Insights, you'll notice there's a long time in there, and I think that's largely because it was a period of waiting to sort out what was going on with these higher level privacy sort of activities. And around the 2000 timeframe, both the funders for human rights projects and the developers of those projects were sort of stumbling over how to address the problems that they were finding. So I think we started to by asking a bunch of questions early that then became even more prescient later. How can funders understand the impact of the ideas they fund without putting their users at risk? How can companies strike the right balance between preserving privacy and driving their development toward making it meet users' needs better? is it really possible to do measurement of digital interactions in a safe and sustainable way, especially in the communities that we were interested in? And can the sort of privacy precepts be upheld for even small projects? So in 2020, mid-2020, there was a symposium held. Internews and ourselves and several other parties hosted developers who were in the open source human rights type communities to look at and try to understand their problems that they were trying to deal with, the demands of their funders versus their deep interest in their communities. And I think these sort of key points came out of that. These are this, and I guess I should point out early that this is kind of a different, a vector of interest into measurement than other vectors might be. So, understanding the patterns of behavior in a way that doesn't alienate users, seeking up a platform for measurement, but one that doesn't harm individuals. There's an idea here that no measurement isn't an option. We need even the smallest projects need to understand their impact or problems with their software. So it isn't an option, and a challenge is if there isn't a safe alternative, then invasive options are easy to implement, and we're in a conundrum about personal safety. The thought process back then also was that if we could increment forward on this, that would be better than waiting a long time for a large improvement. So the outcome of that really is on trying to bring measurement in line with respect for the user. And the idea was to focus on the right questions and getting just enough data to answer those questions. We looked at aggregating on the source. The populations that were interested are very, very largely on mobile devices. That was certainly a consideration. And that we wanted to have something in the path between generator and collector of information that would discard this needlessly toxic personally identifying information. Also, we wanted to make the idea of measurement legible, or transparent is probably the wrong word at this point, but a part of a usage experience that would engage the user rather than alienate the user. And we looked at techniques for generalizing data, de-resolutionizing, what's the right word, for reducing identifiability. I'd like to point out here that also that the ideas like differential privacy were quite solid in the literature starting really in 2006, but it wasn't until the 2015s and those kind of dates when it really became sort of at the forefront to bring into this kind of measurement. So these kind of ideas are still pretty new at the point we started. So we started early. We had a very basic piece of technology that worked back in 2017, and since then we've broadened it a reasonable amount. There are SDKs for both client and server available, and there's an anonymizing proxy that sits between the initial platform we worked with called Matomo, which can be generalized to be used with other analytics packages. And maybe as importantly, we started looking at doing user research to define experiences that made measurement collaborative sort of experience and more obvious for the user, and started on implementations. This diagram here is meant to show the kinds of implementations of clean insights that are possible. The one that's used in a dominant form today is the direct connection, where devices running an operative application for their analytics can connect directly to a proxy that then connects to the analytics engine. But there are also imagined scenarios necessary for us where different kinds of front proxies get involved to assist the user, where there is either censorship, surveillance, or additional privacy needs necessary. Domain fronting can be used here as a very specific term, and then alt is a way to think of other kinds of fronts where maybe Tor is one of those, and there are some other tools being discussed at IETF that can be used in this way. So when it comes to the actual technology we implement, I'd like to first point back to that idea that we were feeling our way initially here, and we're moving from no answer towards some answer and iterating along the way. So what we wanted to start with was a way to do what was the general feeling of normal analytics, that is counting cross tab on some relatively general metrics, doing crash reports and doing surveys. And we felt that if the clean insight solution didn't provide a solution to those basic things, that people would demand or people would use other existing side channels, problematic side channels, to get what they needed. So we wanted enough, a bare minimum of capability without having, but not solving the whole problem right away. In terms of improving anonymity, we looked at batching reports from the client to the server. That has a number of effects, positive on usage of networks in areas that have very deep network problems, whether they're generated by authorities or just problematic networks. And it also hides timestamps of measured activities. We looked at ways to generalize and derez information on the client, talk about that. Domain fronting I mentioned earlier. And we did recognize that at the scales that we're talking about, the number of users of applications, et cetera, that there was a tension between respecting consent and privacy and padding the anonymity set. So that's a sort of detailed part of this, but it was an early criteria about remembering that we have to deal with small scale projects. Another thing we looked at was really borrowing from law, and maybe this is kind of rethinking, again, from the perspective of the user, things about the way measurement has been done canonically and the way we thought our clientele, our community wanted to work on this. So the first is the idea of time-bound contracts, that the notion that you're bound to something that lasts forever. That's a challenge. So we introduced the idea of campaigns, which were ways to put a time binding on when measurements were going to be made. The second was consideration. And this one ties a little bit to the bottom one, which is called contracts of adhesion. The idea that people feel that they must opt in because there's no alternative. There's disparate power between the measuring entity and those measured. And we wanted, and there was often at that point in time, issues with refusing consent meant you're just deprived of the service completely. So we wanted to try to address these sorts of things in the way we did our work when we created a toolkit and a set of best practices for developers. So I think the main thing that we have focused on early, because it is part of the user experience as well as the technology, is this idea of consent. Understanding who's going to use your app, what the app is, what they're going to use it for, and in what situations. We have a number of situations around the globe that put really a fine point on user situations and the difficulty and challenges people have using the internet, especially the communities that we serve, and the challenges that we get into when we're creating network traffic based on simply trying to measure. So we need to start, as we said earlier, start considering about specific questions, narrowing the time that we implement, that we measure, handling the data carefully, and getting rid of it once it's reached its destination and insight has been gained. Working with developers at that symposium, we started developing sort of design patterns around how consent can be handled, and as well as the information needs that developers and funders have. We arrived at sort of principles around consent, and this is sort of the user experience of consent, about making it easy to understand what you're agreeing to, that thing you're agreeing to is pretty obvious and there aren't hidden messages in there, and that saying yes or no doesn't mean giving up use of the application, and that the way we deliver consent is sort of centric around those who need it. So asking for it in the right way, using it in the right way, etc. Here are a couple example models. This is the Umbrella app, and here's an example where This app needs to look at patterns of usage. So it is in fact going to measure different things and connections between things. So it wants to make that obvious that that's going to be what you're consenting to, and then that you're going to contribute for a short period of time. Here, 14 days is the measurement period. On the next page, we have another example, which is talking about collecting metrics, making it feel like a focus group. And again, this is where only a portion of the user base is actually requested, gets this request. And again, a time bound, but a different way to present the idea of consent to measurement. We of course knew that the number of studies we did undertake, the number of groups we worked with weren't gonna span the field for what consent models might look like. So we came up with sort of guidelines and best practices for rolling your own consent. And I would hope that some of these things feel awfully logical and right thinking, I guess you could say. But in fact, the ways that these interact with the different kinds of things that applications do and the kinds of users using applications, quite a bit of thought is required here. We have done a number of implementations, but we also went back and looked at and worked with the teams to look at how did our work out for you. So we actually have impact reports on some subset of the applications we implemented Clean Insights for, and these are the apps here. You'll notice that they are privacy and security related. Again, that relates to our user base. We're sort of going around the world kind of in a lightweight way promoting this idea. Again, since the Guardian Project is fortunate to have a number of software libraries that we've developed that people use of ours, we have a way we're talking to a lot of development teams in the internet freedom space. So we do a little bit drive on these messages related to how to implement smooth and metrics that people can understand and want to be part of. And I think we have started at this small scale, working small, creating a new idea, thinking about metrics in a new way. And that's, I think, the key insight for Clean Insights is that area. Now, on this last slide here, I'd like to talk a little bit about, without getting into a lot of detail, about the commonalities and differences between Clean Insights, which is, again, a fairly, now a 5-year-old project, and what's going on in privacy preserving measurement at the IETF today. Our affinity is that we did identify that proxying was going to be necessary to protect the identity of the user. So we have in our proxy modestly different functionality that exists in the work going on now, or tremendously different in that ours is quite lightweight, and we have a client-server balance between who is implementing privacy. We also like this idea of starting with the questions and the decisions rather than just dumping all the data in raw format onto some server entity. So this idea that there's a collection phase that happens and an analysis phase that happens before eyes are on it, and then the idea of sort of neutralizing the toxicity in data sets that are at rest once they do get to the server. Importantly, I think what we sacrifice is that we are placing some trust in both the collector and on the implementers in terms of knowing what's toxic, being careful about what's toxic, and that there's a best practices way to think about that rather than a structured protocol or tool set that implements those things in a hard and fast manner. And lastly, we do continue to be concerned about the one-time visit, the one-time use, those kinds of problems that occur that really are problematic in our area. Okay, lastly, I've just put up some links here that you can look at. I think the consent guide is a really interesting thing to learn. It's one way to view Clean Insights is that in fact consent is the key piece. So And we also have the code out there and the impact reports if you'd like to look at those. We're at the Guardian Project, and we really appreciate our friends over at Matomo also looking at this problem from a server and analytics package standpoint. So I'd be really happy to take your questions at this point.
Thank you, David. Are there any questions? And thank you for inventing a new word in the middle of your presentation. We have de-resolutionizing to add to the dictionary now.
You know, I also thought that consentful might be flagged out as a new word too, but recently I've seen that elsewhere, so I guess we didn't make that one up.
Stephen, please go ahead.
Yeah. Hi, David. Stephen Farrell.
Yeah.
Thanks for that. That's interesting stuff. I was just wondering, how do you kind of treat something analogous to the kind of right to be forgotten, or when people change their minds about consent, or is that something that you've looked at as part of this project?
So I think my straight answer would be we haven't thought about that. But the other answer, which I think is maybe more in line or a way to figure out, or a way that gives us a tool, is the idea of the campaign. And we do talk about opt out and being respectful of people who don't want to be part of a campaign, and making it obvious that you're asking that, and then and allowing them to say no without, you know, decrementing the function of the application totally if they do say no. So I don't think we have but right to be forgotten, like as if I said yes once, but now I'm not saying yes. I'll take that back as a to-do. That's a great point, Stephen.
Okay, thanks.
Yeah.
Jonathan Hoyland, Cloudflare.
Yeah.
Given that realistically most consent, quote unquote, we get these days is actually just, you know that if you click I do not consent, it's going to be at least 400 clicks before you can see the website. Wouldn't it be better to say, actually, let's push for to reject all tracking must be at least one fewer clicks than accepting? And, you know, then you'd find all these websites where like reject all, the big red button, like, yeah, everyone wants that. And, oh yeah, if I really like this website and I want them to track me, then somebody could in theory do 400 clicks to say, yeah, really, really track me. I'll be up for that.
I'm smiling about that. That's a great point. I think this idea of, you know, we have some in the sort of group that represents this who think that consent has been diluted so badly by the current regime that it's impossible, basically. That for the reasons that sort of Stephen mentioned, for the reason that of the contract of adhesion idea, that the GDPR was initially our friend and now might have been our enemy. You know, there's a lot of issues with the fact that the level of forcing you to give consent can be either hardcore or subtle, but eventually. So I don't think we know how to answer that question at a macro level. What we've tried to do is sort of put tools in place that allow people who, and by the way, we in the mobile area look an awful lot at small scale applications. You know, we have an app out of Guardian Project called Orbot, you know, several million users, but most everything else is below that. And the people who are interested in that are also in a subset. So this is not an internet scale thing. And we're looking at ways, again, starting small to figure out how to try to make consent be real again. I'm afraid I don't have a good overall answer for you, Jonathan, on that.
Right, thank you.
Yeah.
Hi, Conrad Kobrock. Are there any plans to reduce the trust in the collector using cryptography? I understand there are a couple of projects that are working on protocols that try to do that. Is there anything on the agenda for your project?
I would say not yet, but part of the reason I did attend yesterday's presentation on privacy preserving measurement and have been interested in it since it's come up here is that we do have a number of alternatives for increasing the privacy of what we're doing via encryption, for sure. So the oblivious HTTP aspect is one thing. But there are also a number of items possible by implementing more, algorithmic privacy measures on the client as well as on the intermediary. The proxy, the Clean Insights proxy. So yeah, I'm not willing to speak. I don't think I can adequately speak to things directly on the item or on the list. We're just mapping and looking at and making sure the architecture can fit those things as they come along. Differential privacy ideas were thought of early, and we have sort of in spirit versions of that now done on the as part of the toolkit in the client. But there is DP has a very specific meaning, and so I hesitate to use that term in a generic way. I think that's a specific thing that we don't have implemented yet.
Okay, thank you.
Okay. Thank you, David, for the presentation, and thanks for all the questions. We'll move on to the next presentation now. Sophia, could you please try and show your slides?
Yes, I think I requested. There you go.
Okay.
Okay, they are up as I told. Okay, hi everybody. My name is Sophia Selly, and I'm joined today with Daniel Jones. And today we're going to be talking about a paper we published some weeks ago about finding certain practically exploitable cryptographic vulnerabilities in Matrix. You can find the paper online, and this is a joint work with Martin Albrecht and Benjamin Dowling. So first, a little bit of context. We started looking at Matrix because we wanted to actually do a formal analysis and a formal model of Matrix. And in the process of looking at the specification and implementation, we found several practical vulnerabilities, which turned into this paper. But just to give a little bit of context into the people in the room that don't know about it, Matrix is a standard for secure decentralized real-time messaging, and basically aims to do what SMTP has been doing for email. One of the biggest things to think about in Matrix is that it aims to do secure communication in the face of untrusted servers, which they call the home server, in a federated way. And it's very important to think about this untrusted server because this will be our threat model when looking at all of these attacks. And as I said, Matrix uses untrusted server, and because these servers are untrusted, they also allow end-to-end encryption by default on the channels because they are in the face of untrusted servers. One of the flagship clients of Matrix, which people are most often familiar with, is the Element client, which is the people how they actually approach into Matrix through the Element client. But the protocol itself is called Matrix and has been implemented in other applications and clients besides the Element one. So why should we care, and why should we care about these vulnerabilities and in general about doing a formal analysis of this protocol? Is because Matrix and its flagship client, which is Element, is widely used. The website of Element, for example, reports that they have over 60 million users, and the French and the German government are currently using for internal communications and other communications, and also Mozilla and KDE in 2019 announced plans to actually use it. So it's a widely used protocol. As I said, this is a secure messenger, which means that they have certain or claim to try to have certain end-to-end encryption properties, such as confidentiality, integrity, and authentication. And they also claim to provide certain form of forward secrecy, which I think they call partial forward secrecy, post-compromise security, and a form of deniability. In our research, we didn't look at these last three properties, but rather we just focused on the core properties of confidentiality, integrity, and authentication. So it remains as future work that we are doing into actually looking at the more specific properties. Okay, just to give you a little bit of an overview of how cryptography is used in Matrix. So basically in Matrix, you have several parties. You have a user, which often represents a client. And this user has many devices, for example, a laptop, a phone, or something like that. And all of them communicate with each other through the relying of messages via the home server, this untrusted home server that I already talked about. And this home server also is used to store communication history and account information of the user. And furthermore, it's also used to provide a device identifier for the several devices that a user holds. In order to achieve authentication, they use a certain cryptographic identity. There's a master cryptographic identity that is called the master PK, which is the one that is used to provide authentication for the devices that a user holds, and also to cross-sign the devices that other users hold. So you can use all of these identities to, for example, if you're Alice, also verify the cryptographic identities of the devices that both holds, for example. And in turn, each device also has its own cryptographic identity. So you have first user identity and also per device identity. And that one is the one that is usually used to establish the key establishment and encryption channels that are going to be used by Matrix. Those channels are called OM and Megalom. Those are the cryptographic protocols that I use, and I'm going to define them a little bit later. So you want to see how the process of actual verification works is that you have this master public key, which in turn sign self-signing key and also a user signing key. A self-signing key is the one that is going to be used to verify the per device key, and a user key is going to be the one to verify that verifies the list of devices of the other users. So there's this complex protocol in which the different keys cross-verify each other. Okay, as I said, they use OM and Megalom as the underlying cryptographic mechanism. So let's explain first what is OM. OM is basically a way to establish a secure channel between two pairs. So for example, one device with one another. And the reason that they do this is so that they establish a secure channel in which they can share the key material that is going to be used to encrypt its messages during the group chat. What is used on this is that they use a modified 3DH protocol from the Signal protocol and also the double ratchet algorithm from the Signal protocol. They use an old version of 3DH because right now Signal uses another version which is called X3DH, and they use the old version which is 3DH, claiming to have certain deniability properties. And as I said, they also have this channel which is called Megalom, which is basically the group channel in which once you have established an OM channel, a pairwise channel with each one of the devices, then you use these pairwise channels to share the group shared key information that is going to be used to encrypt each one of the messages that you send through the group. And effectively, this is similar to how Signal users send their keys. Megalom also has some ratcheting properties that are very different, not very different, but different to how Signal does the double ratchet algorithm. And the Megalom properties have not been formally analyzed by the community, so it remains to be seen what kind of established properties Megalom actually has. And here just a little bit of diagrams in case you want to look at it more. Okay, so let's go to the meat of the talking itself, which are the attacks. And in this case, I'm going to be defining the first attack, and then Dan will be explaining the rest of the attacks. So the first attack that we have found, we actually call it the attack in which the home server has control of the users and the list of the devices. So why this happens is because you have, as part of a group chat, you don't only send user messages, but you also send group membership messages. So for example, that a user wants to join, or a user wants to be removed, or a user wants to be modified somewhat. But the problem is that neither of any of these group membership messages are encrypted, checked for integrity, nor cryptographically authenticated, which means that a malicious home server can indeed inject any user into the room, and those forged injected users will be able to decrypt any future messages that are sent in the channel. Why do you think that this attack happens in practice? Because we think there was an assumption from the protocol designers, but this is just a speculation. We think that there was an assumption that the only thing that needs to be protected is the user messages themselves, but not these room membership changes. So maybe there was this assumption. And in general, because sometimes there's practical issues when actually trying to implement and actually be encrypting and authenticating these other messages that are not user messages. A second type of this attack is in which, on the contrary, instead of adding a new user, the home server adding a new user, what happens is that the home server adds a new device to your list of devices. So I already said at the beginning is that you use cryptographic identities to verify each one of the devices that you own. So for example, you verify that indeed you own the phone, and indeed you own the laptop. But this cryptographic verification is separate from the list of the devices that the home server maintains. This list of devices that the home server maintains is not authenticated, it's not encrypted, it's just a list that the home server maintains. So therefore, the home server can also inject a new device into this list. And again, this device will be able to decrypt any future messages that are sent through the room. Well, we think this happened for the same reason that we already said in the first attack. And how we actually go on solve these attacks is probably by the way that we will have to use a list that is cryptographically authenticated and is also properly checked. And it's not just a plain text list that the home server controls. And in fact, indeed, we already have such a list because of the cross-signing procedure that I was just describing. Is it too impractical right now that for users? Probably that would be too impractical to have like a list of devices that the user has to individually verify. But for now, that's kind of the best that we have. Okay, now Dan will explain the rest of the attacks. I think you're muted, Dan.
Okay, we can't hear you, Dan. Do you want to just try resetting your audio? We can see you, but we can't hear you. No, I don't think we still can't hear you. So.
Dan, do you want me to continue while you're trying to? Yeah. Oh, there you go.
Okay. We got it.
Ready? Yes. Oh, good.
We can hear you.
Okay, sorry about that. Yeah, so the next few attacks we're going to go through, they vary a little bit in the extent to which they are kind of attacks against the protocol design or maybe the implementation. So like if we muddle those up, sorry. So this first attack, when two parties want to ensure their connection hasn't been tampered with, they probably want to check for like, is there a malware in the middle attack? And they can do this by doing out-of-band authentication. And Matrix provides like a couple of protocols to do this, but the one we're going to talk about now is the short authentication string protocol, which kind of very briefly, the idea of it is that these two parties are going to do a key exchange to kind of generate some kind of shared secret, and then they're going to compare that shared secret out of band. And some of the snidiness of this protocol is you get kind of, they use short strings emojis to do the comparison. And providing they do match, they're then going to send their real, like, correct cryptographic identities to each other over a secure channel that they've constructed using the shared secret. And this works really well in Matrix, but there's our attack targets that final stage where they've got a nice secure channel, but the home server can trick devices into sharing an identity that the home server controls. Well, could you go to the next slide? Oh, nice. Thanks. So like, how does the home server do this trick? Well, first, I'm going to explain there's kind of two types of verification in Matrix. So sometimes you want to verify the identity of another user. So two users are going to do some out-of-band verification together. But sometimes two of your own devices need to also do a verification. And they use the same protocol for this. And for step 3 of that protocol, where they exchange their cryptographic identities, they send a key identifier. And they use the same field for both of these types of verifications. So when you're verifying other users, you send a fingerprint of your master cross-signing key. So it's that MPK field. But when you're verifying devices, you instead use the device identifier. And the problem with that is that that is actually controlled by the home server. So if you go to the next slide, please. Thanks. So then the home server can do this trick where it generates its own kind of master cross-signing key and kind of cryptographic identity for a user, and assigns its fingerprint as the device identifier. And then at some point when two devices perform this out-of-band verification, they're going to send a message, and the device sending the message will send a key identifier. They think it's a device identifier, but the device that receives it will interpret it as a master cross-signing key fingerprint. And this means they'll sign that user identity, and you've kind of like tricked them into trusting a user identity that's actually controlled by the home server. At that point, you can do kind of like an active malware in the middle attack from then onwards. Oh, cool. Next slide, please. Thanks. So what causes attack? Well, it was effectively just like a lack of domain separation between these key identifiers and the device identifiers, using them in the same place. And in general, I think it would be really great to, like, in the future, just avoid using server-controlled inputs in these kinds of out-of-band verification protocols, because it would just helps with kind of cleanliness. Oh, and then the next slide, please. Thanks. Oh, cool. So for the next attack, we're going to talk about, we've called it the semi-trusted impersonation attack. And the idea of it is when a user adds a new device, they'd like that device to be able to decrypt messages previously sent to that user. And there's this thing called the key request protocol that Matrix kind of provides to do that. And here we can see on this slide, Alice's first device on the left receives a message it can't decrypt, so it sends out another message asking for the decryption key. Alice's second device sees this request and it checks a couple of things. It goes, well, is the requesting device a verified device from the same user as me? Or have I already sent this kind of decryption key before? And if it passes those checks, they'll encrypt using an OM channel, a forwarded room key message is what it's called, and they'll send the decryption key to Alice's first device. And as part of that message, they'll include the identifier of the device, that kind of the claimed owner of that key. And that, for that reason, it's really important that you check when you're on the receiving side, do I trust this device that has sent it to me? And this is where the checks were missing. And so if you move to the next slide, please. Thanks. So what the attacker can do, what a home server can do, is they can create their own device. They can generate their own room session, their own mega-ohm session, and they can just forcibly send a forwarded room key message to Alice's device, pretending to be, say, Bob's device. And Alice's device would just kind of accept it. So this was this kind of attack worked in practice, but it is a little bit weak because all keys that arrive via these forwarded room key messages will be flagged as like kind of semi-trusted. So you can impersonate on the mega-ohm channel, but only in a way that's kind of like flagged in the user interface. Oh, I'll switch to the next slide, please. Thanks. So what caused this? Well, it was effectively just an implementation mistake. But as a general kind of like, well, this is my reading of the situation. The key request protocol was a little bit underspecified in that it didn't talk too strongly about like why, what to do on the receiving side, and similarly what to trust. Like it kind of leaves that up to the implementer. Like when should you trust these forwarded room key messages, and when shouldn't you? So I think like a more prescriptive specification would have helped there. Oh, cool. Next slide, please. Thanks. So now for the next attack, we're going to talk about a kind of a slight upgrade to this. So when you have a mega-ohm session set up, you initialize like a mega-ohm, an outbound session, an inbound session, and a signature that kind of links them together. And you send these over like the ohm channels as before. But knowing that we can kind of do the semi-trusted impersonation attack over mega-ohm, the question is, can we use this kind of, if we can send these messages, these session setup messages over mega-ohm instead, we can kind of upgrade our impersonation attack to one that isn't kind of tagged as a forwarded key. And that's what our attack tries to do. Also, if you go to the next slide, please. You can see here what we try to do is we start off, the home server is trying to impersonate Bob to Alice. And it first starts by doing the semi-trusted impersonation attack. And at this point, the adversary can send Mega Ohm messages that verify as being from Bob's device. They can then generate a second Mega Ohm session. We've tagged this G star, and they send it using a normal session setup message. So it's not a forwarded room key, but they do it over Mega Ohm. And this is kind of where the protocol confusion and where the main implementation mistake was. And by sending it over Mega Ohm, it kind of passes all the checks that say this is a verified, this is a verified message from Bob's device over Mega Ohm. And from this point onwards, it kind of gets tagged as a session and you can use it, but it's not tagged as like a forwarded one or anything like that. So you kind of get a slight upgrade. Oh, cool. On to the next slide, please. Thanks. So then for the next attack, and the final one we're going to be doing in this presentation, is the kind of a confidentiality break that extends the issues we just talked about by looking at two new subprotocols. So the Mega Ohm key backups protocol allows inbound Mega Ohm sessions, so kind of like the decryption keys, to be backed up on home servers. And then they're encrypted on home servers using a recovery key that's kind of shared between the user's devices. The second subprotocol we're going to talk about and use is the secure storage and secret sharing protocol, which allows users to back up account level secrets and also to share them between their devices. So this is things like cross-signing keys, and actually the recovery key that Mega Ohm used for Mega Ohm key backups that gets synchronized using the secure storage and secret sharing protocol. So in this attack, what we do is we utilize that protocol confusion and semi-trusted impersonation attack from before, but we impersonate a trusted device and use the secret sharing functionality to force the target device into using a Mega Ohm key backup that the recovery key, using a Mega Ohm key backup and use the recovery key for them that is actually under the home server's control. So we kind of impersonate a trusted device and send a recovery key. And then what happens is the target device will then start uploading all of the decryption keys it has encrypted on the home server, but with encrypted with a key that's under the home server's control. And at that point, you can kind of decrypt these, decrypt all the messages that this target device has access to. Oh, cool. And then if you skip forward again, sorry, I'm just gonna, thanks, yeah. So what caused this? Well, again, it was an implementation mistake. And the main one was this protocol confusion. But there are ways this could have been kind of maybe avoided a little bit or discouraged by the specification, because they push quite a bit for a kind of like pluggable and replaceable encryption algorithms, which means that kind of that's reflected in the code architecture. But different algorithms have different security properties that change how they can be used securely. So maybe a more prescriptive and less flexible specification might have helped avoid this kind of like this kind of code issue. But yeah, it's definitely an implementation problem. Oh, thanks, Sophia.
Okay, so just a little bit to give you a little bit of a conclusion. So what's the lesson learned that we learned after looking into all of these vulnerabilities? First and foremost, that they are practically exploitable. We even have a proof of concept that indeed they can be practically exploitable. We don't know how much they're exploitable in the wild. And some of them have been fixed by the Matrix specifications. Some of them will be fixed in the future, and some of them might not be fixed. The reason why Matrix did all of this protocol is because it's a really complex thing to do properly secure messaging, group messaging protocol, as we have experienced already in the IETF with MLS. It's not an easy task. And then the other easy task on actually thinking about group messaging is to actually think what kind of properties it should have. And that, at least from the specification of Matrix, sometimes is not unclear what kind of specific properties they aim to provide. So that's what is the conclusion of this, that we need actually a formal model and analysis of thinking of this protocol, and perhaps also understanding and taking inspiration from protocols as TLS and MLS, in which there was a collaboration between the academic community, standardization body, formal verification community, to actually provide protocols that actually had a good threat adversary model in mind, and also the specific properties that they wanted to provide, and a formal proof that indeed they achieved said property. So we want to have a correct group secure messaging protocol that is interoperable as well. Then we actually need to do the work of actually sitting down with several people from several communities to provide a safe protocol. With that, I will just skip these other slides, and thank you very much.
Thank you both for an excellent and very sobering presentation. I think you have certainly answered the question, secure group messaging, what could possibly go wrong if we didn't already know the answer? Thank you for your teamwork on the presentation as well. And I'm hoping we have some questions. Okay, we do. Stephen, you're up first.
Hi, Stephen Farrell. Really good work. Thanks for doing it and reporting on it. I just had a question. Did you have or did you spend any time looking at the federation between home servers, and are there any issues there that you found or that might be interesting?
Do you want to take? Do you want that?
We haven't. We kind of modeled it completely as kind of all the home servers are a single entity, almost like a single untrusted entity. But it'd probably be good to do that. I think there is a cool paper that looks at the synchronization algorithm, the state sync algorithm, but I can't remember the name of it.
Okay.
And it was,
sure, if you could think of it and put it in the chat or mail, that'd be great later. Thanks.
Yeah, Rafa Robert. Yeah, so my question is the same vein as Stefan's. Do you plan a sequel?
You wanna go, Dan? Well, I think we will say the same. So you go.
Thank you. Yeah, I think our plan is we're working on some formal modeling and those kinds of things. So that would probably be like the natural follow-up, is to try and show that now that Matrix have fixed like the vast majority of these issues, and they did it really fast and they were super responsive. Yeah, just trying to show that now, we can get to a place where we believe it's nice and secure.
Some of the work that we have also been thinking is to actually understand what kind of deniability properties they aim to provide. It was a core aim of the Matrix protocol to provide deniability, but it has not been also formally modeled. So we will also be looking at that.
Hi, Mr. Bertola. First, well, thank you for doing this, first of all. I want to check if I got it. I mean, are these the same vulnerabilities that were already discovered and released in September, and I think fixed already in a good, at least for most of them, I think there's a disagreement on one. So just to check if these are new ones or if are the same that were already disclosed. And the other thing I also wanted to say, I don't know if you were this morning, if you attended the MIMI meeting, but yeah, it's very important that now you go there, because I guess in the future we might converge on other protocols, not on all MEGOM, and it's very important that we get them right. So.
Yes, they are the same vulnerabilities that we disclosed. There's not anything new in this presentation besides what we already disclosed. I also attended the MIMI now future working group, and I do hope that on those of them we do take the same lessons learned that we have from MLS and TLS 1.3 of actually making a group that has a collaboration between the academic community, formal methods, and standardization body to put out there something that's really safe and good.
Thank you again for the presentation. And if you do part 2, please bring it back here and present it to us again.
Thanks.
Oh,
Is that a very quick?
Sorry, was there one Q question that we missed?
Not a Q question, just with respect to the formal analysis points on the last slide, there's a side meeting in Richmond 6 tomorrow on doing formal methods. Woo!
Thank you for that gratuitous plug. Okay, so we'll move on to the last presentation we have, and this is by Simon Basso of UNI. Some of you may have seen the brief presentation that was given yesterday, I believe it was, concentrating on censorship in Iran. And this is a much more general talk about measurements of internet censorship globally. Please go ahead, Simone.
Thank you. So it seems you can hear me. Hello. Okay. First of all, thanks for inviting me. I'm very happy to be here. So I want to basically provide you an overview of what UNI is doing for measuring censorship. And I would like to focus a little bit more on measurements of encrypted protocols. And I also want to focus a little bit more on the more experimental stuff that we are doing, as opposed to like the mainline measurements that we are doing. So let's say a few words about UNI first. So it's a free software project. It started in 2012. Like, the idea is to provide people with tools that they can install on their phones, on their computers, and use those tools to measure internet censorship. And the over time, we have collected more than 1 billion network measurements in more than 200 countries. The way in which it works is that you have this application for mobile or for desktop, or a command line application, and you can choose what category or which tasks inside the category to run. Our, in a way, flagship experiment is the one for websites, where basically there is a list that the probe is going to measure, a list of websites, which depends on the country in which you are in, or if you want, you can choose custom websites for you to measure. And this will be part of what I will be talking about in the presentation. I will not focus much on instant messaging. I will just say that we have these specific tasks for instant messaging apps where we measure endpoints that matter to those apps. As for circumvention, again, I will not be focusing on it here, but briefly, and I think it's also related to previous conversations I've seen in the chat, what we have is we integrate Siphon, which is a circumvention tool, and so our task bootstraps Siphons and tells you how much it takes. We do the same for Tor, the vanilla version, so without any pluggable transports. We also integrate Snowflake, so we can tell you how much it takes to bootstrap Tor plus Snowflake. So, and then we have also other kind of tasks that, so for example, performance tasks and middle box tasks. And then while those are the tasks that are part of the application proper, there is a huge amount, well, not a huge amount, but a few experimental tasks that do not run all the time, or just run sometimes in background if you enable them. And those are part of what I'm going to discuss in this presentation. Okay, so now I want to spend a little bit to explain the principles with which we measure. And I will use as an example here measuring the web, though measuring encrypted DNS is similar as a concept. Not all the experiments that we have are at this are following these principles. It took us experience to understand these principles, and so only the most recent ones follow these principles, though they are the ones that either we are using the most or we plan to be using the most, so that's basically fine. Okay, so the first part is that we want to provide the probe to measure we want to provide the probe websites to measure. And that is a URL, but providing the URL in itself is not enough. We need to know more about that URL. It's important to know in advance what are known good IP addresses for that domain, which helps us to find out more ways in which a website could be censored. And then we also have ways to know more or less around the same time that the probe is performing a measurement, whether the website is expected to be up and it's expected to working as intended, basically. Okay, so that's the first bubble, basically, the target to measure and contextual information that helps with measuring. Then there is the first act of measuring, which for web is a DNS lookup. So we in most cases, and historically, we tended to use get_info, and the reason for that is that in many countries, so for example, in Italy, where I'm right now, and many European countries, most censorship, or historically, most censorship has been implemented only by the resolver of the ISP. So that's the historical reason why we use get_info. We don't always know what the resolver is. Sometimes it's easier than other times to discover it. And so that's a way to use that. But more recently, we started to add in parallel another resolver, and this one is using the DNS unencrypted over 53 UDP. And the reason for that is that in some cases, get_info may be using an encrypted channel. So for example, we know that with systemd you can use DOT, etc., etc. And then what the additional unencrypted query allows us to know whether there is a blanket interception or tampering with DNS requests, which seems to be the case in most countries. So it's quite uncommon that you have targeted filtering for a specific server endpoint. In general, it's for all queries. Okay, that part of our measurements give us IP addresses or errors, and generally errors are like, wait, what? We didn't expect this, because in most cases we know that the website should be have IP addresses. So in general, when we see something unexpected compared to what we know to be true, we call this an anomaly. And then for IP addresses, we are not sure whether they are good for the domain, but when we are measuring encrypted websites, we say they are good if we can TLS handshake with them, because we bundle Mozilla's CA. We hope there is no rogue CA in there, and surely there is no extra CA that the user may have. So, okay. Okay, once we have a set of IP addresses, which is the set that we already knew plus the one discovered by the probe, then what we do is basically construct endpoints from those addresses, and then we do what is required to do so for HTTPS. That's mostly TCP connect, TLS handshake, and then trying to get the resource. And each of these operations could fail, and then if we expected it not to fail, if it fails, we are again into the, hey, this is an anomaly territory. So yeah, those are the principles. And users run UNI, and then there is a backend, and the backend is actually very important to us, even though users do not see it, and it organizes measurements, and it has an API. And through the API, and through a website called UNI Explorer, researchers, including us and users, they can fetch measurements, and they can also not only fetch individual measurements, but also group measurements, and try to make sense of measurements, like looking at charts that show trends in general. Slash reports is where we publish reports on our websites. And now that I think I covered all the basics, what I want to do is to so basically discuss a bunch of recent works that we did, but rather than giving a broad view, I want to show some aspects that I consider interesting that we are working on, that we found, etc. So the first report I want to focus on is this one that was about Iran. And so this is about the Masa Amini protests, and it was at the end of September of this month. And there was already lots of disruption in Iran before the protests, but something changed around the protests. And so, for example, here we have a math chart of DNS over HTTPS. Each row is a service, and each bar in the chart is its height is the number of measurements collected on a specific day. And then it's divided in different colors, and each color is a class. Okay means everything, literally everything was okay. Then we have anomaly. I told you already what anomaly means. It means basically we expected something to happen, but there was a network error we didn't expect. That's mostly what an anomaly means in this context. And then confirmed. And confirmed in general means that there are signatures, known signatures of censorship, and we found some of those signatures inside the data. In the case of Iran, that mostly means Bogon IP addresses that are known to be used to implement censorship. Now, if you see basically the colors trend here, you see that after the 21st, for most services, it changes from yellow anomaly to red confirmed. What I wanted to do here, which is a bit more in depth, I wanted to show you what happened for DNS-apple.com on the 24th. So next slide, cool. Okay, so when I told you our principles for measuring, I told you that we provide the probes with known good IP addresses. This means we can, regardless of what happens for DNS, we can check whether we can establish connections with known good IP addresses and see what happens for that. Okay, and this table shows that. So the first column is the S number, the last column is the number of times something happened, and the other columns in the middle allows us to classify how many times we did see specific blocking patterns. So DNS means DNS was blocked, and TCP means TCP was blocked, etc. Okay, and success means something was okay. And and like for ZTAL, for example, the first row, the DNS always failed, and it always failed with one of the three bogons shown above. So that basically means that if you just use the DNS, local DNS, either the getter info resolver or UDP, you will then not be able to go further. But we provided the probe with IP addresses, and so when we use those IP addresses, we always failed in the TLS handshake, and we failed with this signature that you send the client hello and then nothing happens, and then eventually you time out because you're tired of waiting. Another network, TCI, had a similar pattern. Again, DNS blocked the same way. However, the good IP addresses that we provided to the probe failed in two distinct ways. So sometimes it was timing out during the TCP connect. For other, let's say, more lucky IP addresses, instead, you were able to establish a TCP connection, but then you were still timing out in the TLS handshake. And that happened 21 times, but 5 times it happened something that is quite interesting. A few of those IP addresses that we provided, they were actually working, so they were succeeding, and this suggests, and it's not the first time we have seen this happening in Iran, that there is not just a some if in the network that if the SNI of the client hello is such and such, you are blocked. It's a bit more complicated than that. It also depends on the IP addresses that you're using, and it's dynamic. So probably depending on what people do, that's a speculation, but I would suppose that seems, I mean, that's my mental model of what I have seen, basically, that it depends on what IP addresses are used, and it seems to change. Okay, so this is it for this specific case. Now, another case was this study we did for Russia at the beginning of the war. And again, I'm not going to describe the whole case. I just want to flag something that I found quite interesting. So at the beginning of the war in Russia and Ukraine, what we did see in happening in Russia, what many people did see, is that Twitter was very difficult to use, and so the conclusion was that it was throttled, and many people published about this. And we also published about this, and the way in which we saw that there was this form of throttling was like this. So when we are TLS handshaking, we record the time stamp and the amount of bytes received by Raj. And then by collecting this data, we're able to say at the end of the handshake, regardless of the result, how much data we were able to fetch in how much time. So basically that's the speed, and the handshake size is more or less the same in the sense that you need to fetch the same data like certificates, etc. So what we saw was that you can there was two populations, basically. A population of users for which the TLS handshake for Twitter was at, let's say, the speed that we could saw before this problem, so at the beginning of the chart, the 24th of February. And then suddenly on the 26th, some users instead were having these very slow handshakes. And then if you go and look, you see that those measurements with the very slow handshakes, they were timing out in the handshake, or timing out or trying to fetch what we were trying to fetch, which was an image. So that was the way in which we detected the signature of throttling in our data. It was not something that we planned for. We actually added this data collection part because we thought it was useful, but we didn't think about throttling. And that was fortunate that we did this. And now what we are trying to do is to have something similar also while we're fetching the body, which will help us to detect this form of throttling. And I guess the message here is that the kind of throttling that you would expect when you want to disrupt something is very, very heavy, because in a way you want to be below a certain bandwidth that makes it very difficult to use the application at the end of the day. So, okay. The third aspect I want to focus on is that so far I basically discussed only TCP-based measurements. However, we have been starting to look into QUIC as well. And while the mainline website measuring experiment does not contain code for QUIC, we have experimental experiments that we have run in some cases that do, and we are looking forward to merge those into the mainline experiment. And so, again, I am not going to discuss everything. I just try to discuss something that we were trying to look at. This was run from China, and we had this opportunity to basically have a list of websites that were available with HTTPS or HTTP3, and we tried to test like both. And the idea was to see what happens, if something is blocked for HTTPS, what happens to the same website on HTTP3. And so there is this basically diagram where on the left we have the clusters of failures: connection reset, TLS timeout and shake, success, and timeout while connecting TCP. And those translate quite neatly to other categories that matter for HTTP3. So for example, other, which honestly I don't remember what it is, but was very rare, success, and quick and shake timeout. So what we already knew, and was a bit confirmed by looking into this, is that in China, it's very, very common to block IP addresses. And we were not sure whether, and honestly, we cannot be able to say it's IP addresses or endpoints, but certainly the endpoints that were blocked for TCP were also blocked for UDP. You see that like this 24% fraction translates to a more or less equal fraction for QUIC. Instead, the majority of the sites that were blocked with connection reset or timed out during the handshake, they were actually accessible. Now, this is not recent. It's 6 months. No, it's 4 or 5 months ago. So maybe now it's not exactly the same. It could have changed, though. At the time, that's what we were seeing. Okay, so we were asking the question whether, okay, but is this really that they are blocking the 443 UDP endpoints, what it is like? So we created this other small tool called QuickPing. And so the idea of QuickPing is that we want to decouple in a way the fact that Quick is like embeds the transport part and the TLS part in the same packet in a way. So we sent an initial quick packet, minimum size, and the part that should have been TLS was random, but we sent a version negotiation that was, if I recall correctly, BA in hexadecimal. So that was invalid. So the idea is that we send this invalid packet. And because the version is invalid, we expected to receive something. And at the time, at least, that seemed to work, as like we were receiving pingbacks from servers. So we tried this in that context. And what we actually discovered is basically that no, as far as we could tell at the time, the timeouts that we were seeing with HTTP3 on the left were mostly timeouts for pings. So it did not seem at the time this was basically caused by inspection of the TLS part of Quick, even though, again, Quick is a new protocol and time flies, and so maybe now it has changed. So, but yeah, at the time we didn't notice this kind of potential interference. Okay, now this is the last topic to touch upon, the DNS check experiment. So this experiment follows the philosophy I described you at the beginning, like the way in which we try to organize measurements. So there is nothing really new to say here, but that there is an experiment in UNI that is dedicated specifically to measuring DOT and DOH. And that experiment tries to follow this principle of providing the probes with IP addresses that are good for the domain. So we are happy that we, even if we are DNS censored locally, we have good IP addresses to try. And the other good news is that this experiment is now in Uniprobe. And like as I mentioned before, in the Uniprobe app, there is a section called experimental that you can run manually, or you can ask the Uni app to run it automatically along with other tests. And so we now start to have data about this, even though we have not looked actively into this data because, well, we are a small team and yeah, it's like recent months have been very bad in terms of censorship. So I've always wanted to look into this, but I could not do much so far. Though what we can do and what we are working towards doing right now is we are trying to take our, let's say, scripts that we use for writing reports and convert them into tools that everyone can use with UNI data. And so these charts here are produced by these new tools. And what I find quite cool about these new tools is that they explode measurements. So like every experiment produces its own kind of JSON measurements, but these tools, they like unpack them. And so every experiment needs to do TCP connect, and it's in the same way. And TLS likewise. So they will create those tables that all experiments will end up filling TCP tables and TLS tables, etc. And so now we are able to do stuff like, okay, give me all the TLS connections that we have for this domain, regardless of the experiment. And then, of course, those are the ones that arrived to the TCP point. So you need to have TCP that has been worked at that point. But yeah, so that's something we are working to do. So here is data from DNS check. And I tried to like, yeah, basically the meaning of the rows is Cloudflare DOH domain means the URL that you would use for Cloudflare DOH, which is quite long, so it was not fitting in the chart, etc. And we tried to provide like a view of what it was looking like 10 days ago or something for China, Iran, Kazakhstan, Qatar, and Saudi Arabia. And that is just connections that are at the TLS stage, and they are trying to TLS-centric. And then another thing we are trying to improve on is we are trying to, rather than providing this yellow anomaly, which is a bit like of a container for anomalies, we say, okay, this is the kind of failure that we have. So it's more interesting to know, like you can directly see the fraction of connection reset or timeouts. Okay, I'm concluding. So the final thing I wanted to mention is that we are trying to improve, and I told you already ways in which we're trying to improve and analyze our data in a better way and make this available to everyone as opposed to being just tool for us. Other stuff we are working on, I would really love to have better DOH3 and DOQ support for DNS check, so we have better data about those as well. It's very important to make sure we are using the I would say the Chrome browser's fingerprint, because currently our tool is Ingo, and the fingerprint that we have is not the one that Chrome would use. And sometimes the Go fingerprint is associated with circumvention tools. So we want to remove confounding factors here. That's another thing we want to do. Then we want to integrate Quick into the mainline experiment. That's, I think, yeah, those are the most important things we want to do. And with that, I think we reached the end, and I'm happy to take any questions.
Thank you very much for the excellent work and for the great presentation. We'll open the queue for questions now. Yeah, can you state your name? You're not in the
Yes.
Mitato queue.
Thank you. I'm Marco Davids. I work for SIDN. Thank you, Simon, for this interesting presentation. I have a question. I was wondering, are you interested and do you look at the root cause of any blocking of internet access? For example, our company's website, SIDN.nl, is blocked from Iran, but that's not because the Iranian government or anything has decided that. It's because Google Cloud Platform has decided to block traffic from Iran to their customers, which we are one of them.
Yeah.
Is that relevant for you, that kind of distinction between who is blocking and what the reasons why you cannot access from a certain country to a certain site or location?
Yeah, so excellent point, excellent question. It is not something we can, as far as I know, measure directly with our tool, but indirectly we can, in the sense that, yes, we are aware of that problem. We have a community of users and they have raised this problem with us. So we try, when we analyze and produce reports, to always keep that in mind. And my recollection is that the way in which it is blocked on Google is that you got a 403. So
that's correct.
Yes. I would say that we can see that in the data because you don't see a connection reset or timeout, but you see a 403. So
in fact,
it's in the radar.
In fact, you even see a valid TLS connection, so that might also be a hinge.
Yeah. Yeah. So thank you.
Yeah, thank you.
Next in queue, we have Alex.
Hi, Alex Shanowski, Google. I was wondering if you're planning any extensions to your quick ping tool. From quickly looking at it, it looks like you're only sending like the version negotiation aspects. And one of the things that I believe we've seen in the wild is that there are some middle boxes which look at specific offsets because they don't understand quick. And therefore, if they are looking for things like, SNI, which I think moved between draft 29 and RFC, then they end up blocking because they're trying to allow list on things in the public handshake, which means that I believe your quick ping tool, if it doesn't consider that sort of case, would erroneously say that the connection is allowed. Whereas if you actually try to establish a full quick connection, it would get denied.
Yeah, so I'm happy to be here because there is people like you that can tell me this stuff that I was not aware of. So I'm grateful. No, we are not doing that. We should. And actually, if we can get in contact with some of the contacts that it's there, I would love to know more and improve our tools. Thank you.
Next, we have DKG remotely.
Hello. Thanks for this presentation.
You're really quiet. We can only just hear you.
Thanks for the presentation, and thank you for all the work on Uni. If I'm blasting out the speakers, I could turn it down further. I was wondering if you have any insight, or if you can share any insight into the decisions you make about what to gather. In particular, I was just testing the Uni probe, and it identified some blockages, which I'm not sure are correct. So I'm trying to figure out. I'm looking at the data that it gathered. And I noticed that some of the things will say, this test failed in this way, and other tests like the SSL unknown authority response, I believe actually sends the peer certificates that were gathered. So you're actually building, or you're retrieving a data set of those things. I'm wondering how do you think about how much information do you want to take versus, like, it's useful for identifying technical roots, and then some of it might actually cause problems for the users that you're gathering from. I'm wondering if you could just talk a little bit about how, to reflect the question, the first talk of this session, David Oliver's talk about how do we gather measurements in a responsible way? I'm assuming you guys have thought about that, and I'm wondering what's Uni's approach there.
Gotcha. Yeah. So I actually did not mention this, but there is documentation about what we collect, and when you install any tool, including the experimental command line client, it tries to explain in a concise way, and it tells you, look, we are not an anonymity tool, quite the contrary. So your traffic is traffic that may stand, and therefore you should read our basically informed consent documentation if you consent with that, yeah, and then it's much nicer in the mobile apps or in general in the desktop apps, because it tries, yeah, like it's not a command line tool, so it tries to give you like more. And also another thing that we do is that after we provided these bits of information, we ask to the user questions like, is Uniprobe going to do X, Y, Z? And they need to say true, false to demonstrate that they have understood what the tool can do. I don't remember by heart the exact questions, but something like a question could be like, if you're using Uniprobe, your ISP could see that you're using Uniprobe, true or false. And if the user says false, we pop up and say, no, look, actually, that's not the case, because Uni is a measurement tool. It's not like that. So we try to educate the users, and we try to have documentation about what Uni does at different levels of complexity. And we also have, I mentioned that we have experimental experiments, and that's part of why we have experimental experiments. So you cannot run experimental experiments with the normal client. You need to download the specific client, which is not super advertised. So you need to know what you're doing if you run experimental stuff, which means you are self-selecting yourself already. I hope this answers to your questions.
Yeah, thanks. I thought it was interesting to see the pop quiz approach to trying to confirm that the user actually understands. I thought that was an interesting thing, especially given the earlier talk. Thanks.
Cool, thanks.
We're a little bit over time. Is this a very quick last question? If you can, can you take it to the chat or to the list? And that'd be great. So, okay. Thanks again for the presentation, Simone.
Thanks.
That's everything for our meeting today. Thank you all for coming, and we hope to see you next time. Thank you.
Thanks all. See ya.
Yeah, it was great. You can't join for the dinner?
I can't tonight. No, I had something else on just at the beginning, and I thought I'll just leave it this time. So yeah.
You'll be missed.
Yeah, it'd be good to come, but I haven't been for years now.
Do you know what happened last time?
No.
We'll talk later.
Okay. What time are you heading out to that?
7 p.m.
Okay. So, because I'm going to be in the bar between 6 and 7. So if you happen to be around, do you want to grab a beer then?
Yeah, that sounds great. Yeah. When is the plenary?
It starts at 5 till 6:30.
Okay.
Or is it?